So let's start the second session in the morning. So the session consists of two talks. Both are about finite automata. So the first talk is by Dr. Tomoyuki Yamakami. Yeah, please.
Okay, good morning. Well, this is about quantum computation. Particularly, I'm talking about the model called finite automata, quantum finite automata, or QFAs. So this is just a summary of my talk. The talk consists of several topics. Particularly, I'm focused on the non-uniform state complexity. State complexity is the one of the complexity measures and how big or how complex the finite automata is. I'm going to explain this in all the detail in later talk. And particularly, I'm interested in relativization. So putting the oracles to the base, the underlying, the basic, the machine model. And I'm going to explain about the roles or the behavior of the oracles when they are actually attached to the finite automata, quantum finite automata. And also, so I'm talking about different models. For example, the deterministic or probabilistic finite automatas in comparison to the quantum finite automata. Particularly, I'm interested in polynomially many internal states. Those are the keys in this talk. And so I'm going to construct several oracles, recursive oracles, to show the inclusions and the separation of the complexity classes associated with based on the quantum finite automata. So first, I'm going to explain about the models, the basis models. So this is the quantum version of the finite automata, or the QFAs. The QFAs are introduced in the last few years of the 1990s, and the convex and lattice and the Moores and the crash field, and they introduced the basis model of the quantum finite automatas. Later, several researchers expanded the idea or the basis model of the QFAs, adding some more functionalities or putting some restrictive use of the measurements and so on. When I say that one-way quantum finite automata, the head always moves from the left to right. I'm going to use the two end markers. So the head actually moves from the cent mark to the dollar sign. And when I say that a two-way quantum finite automata, head always, either the head moves in both directions, to the left, to the right, or I allow the head to be staying still while taking a stationary move. Okay, so this is the base model, so-called the QFAs, and particularly I'm going to supplement the so-called garbage tape. The garbage tape is related to the kind of the environment, external environment that's surrounding the machines or quantum systems, and whenever you need the information, I process all the information instantly. But then if I don't need some information, well, here we don't have any memory space, so that we can't keep all those unwanted information. So we simply throw it away to the environment, just to put the information outside of the quantum system. So to explain that environment, I'm just simply using the tape, so that you can actually dump the unwanted information, but you never read it. Because if you read it, then you can actually use the tape as the memory space, right? That is not allowed for the quantum finite automata. Okay, So here, so I'm using the the garbage outlet. So that's that's slightly different. And also, instead of using the transition function, I'm going to use the transition table. Okay. The use of this in the garbage tape is not very new. Several researchers actually published the papers using this model. And also, more technically speaking, this model is equivalent to the basis QFAs with mixed state. It's not the pure state, it's a mixed state, mixed quantum states. And the operator called them super operators or quantum operators. Okay, so this is the explanation of the transition table. Well, I'm using it in a transition table instead of the transition function. There is some reason. Well, I'm going to explain that reason later. So the transition table is just a matrix or a table that actually specify the value, or we call it an amplitude of the transition. For example, if the machine is in a state Q, so this is the inner state or internal state, and reading sigma on the input tape, and then in a single state, their state is changed from the Q to P, and the head moves in direction D. So the D consists of the -1, +1, and 0. 0 standing where the head doesn't move. So this particular transition has this amplitude. The amplitude is somewhat equivalent to the probability, but slightly different, because we are actually using the norm, the different norms. Okay. So this is the called transition amplitude. Now, so here is an illustration of the 2QFA. 2 stands for the two-way. So we have the input tape and we have the garbage tape. And input tape holds the classical information, like if you are using the binary alphabet, then 0, 1, 1, 0, 0, something like that, right? Head moves in both ways, and also then we allow the head to stay still, right? Now we have the finite state control part, the CPU part, and also then we have to keep tracking the position of the head, and also we have to actually keep tracking of the head position. As I said, the garbage tape is not the memory. So whenever you write something, then the head always moves to the right. They never goes back. So this is called a write-only tape. Right? And we have the transition table. So this is the program part of this machine. Right? Whenever we, the instruction, we just access the program. And the program tells you what to do. Right? Okay. So now, you see that this part is classical, but the head position, here. So that is quantum. And also the state. Right, the internal state. This is also the quantum state. And then the garbage state position is also quantum state. Now then you can possibly throwing away the quantum information. So the garbage state contains the quantum state. So that everything except the content of the input tape is quantum. Okay. There are several restrictions. For example, you can actually take the head position to be the classical, or internal state must be classical. Well, then you can think about it a whole bunch of variation of this model, right? Okay. Now, then I'm going to explain about the state complexity. But then a particular kind of state complexity, so-called non-uniform state complexity. This is actually in comparison to the standard uniform model of state complexity. So state complexity basically is the expression of the complexity of the description of the finite automata. basically in the finite automata, the size of the finite automata is based on the number of the inner states. So simply take the number of the inner states, and we call it the state complexity of this particular machine. Right? Now we can think of the family of the finite automatas, or generate the finite automatas. Right? And the n is the index or the parameter associated with this with the family. Right? Each family has the form like this one, and we use in the transition table and also garbage alphabet. Those are slightly different from the standard model. Right? Whenever I talk about it in the classical model, then you just simply forget about the garbage tape. Okay. So the state complexity of this family is now turning to be a function in n. N is the parameter here, right? So if you have the two families of the finite automatas, and I'm going to say those families are equivalent if all the corresponding machineries they actually produce in exactly the same languages. Okay, so we have a family of machines, right? Now we are going to introduce the family of problems. The promise decision problem is the pair of sets, right? A and R, and the A consists of the accepted strings, and R consists of the rejected strings. So we are actually separating the yes instance and the no instance, and also we have something else, but we don't care about what the outcome of the machines. Right? We are only interested in yes part and no part. That's it. So the string x is called promised if x belongs to either yes instance or no instance. So we are only interested in promised strings or promised input. So the machine solves this pair or the promised decision problem if the machine correctly accepts input x whenever x belongs to A. And for all x that belong to R have to be rejected. But we don't care, as I said, we don't care about not promised strings. Not promised strings. So now we can think of the family of such problems, right? And the family of the finite automata is said to solve this family of problems if the n sub n. So n is an index or parameter, right? Therefore, given n, the nth machine solves the nth pair of this promise problem. Right? Now, we actually have the families of the problems, the family of machines. Right? But we don't care about how those machines or languages are arranged. So that means we have a non-uniform setting for the the problems. The word of non-uniform is coming from that reason, from that situation. So non-uniform state complexity is not really new, and the Berman, Lingus, and Sudokus, Sixer, they started considering non-uniform state complexities. Particularly, they actually interested in polynomial state complexities. So that means that the given parameter n, so we have n to the k many internal states. Right? And after some period, and Computation and Pizzini, they kind of revitalized or revitalized the study, because there is roughly 30 years in the kind of the period that nobody is paying much attention to the concept. But it turned out it's very interesting because for example, I'm going to explain the things later, but if you think about the deterministic case, like deterministic polynomial non-uniform state complex, and non-deterministic version of it. So we have a deterministic version and non-deterministic version, right? So now we can think of whether the two concepts are exactly the same or not. But so far, we have no proof proving or disproving that the two concepts are exactly the same. But that question is something to do with the logarithmic space complexity, L and NL. But anyway, so later on, I discovered some relationship between the non-uniform state complexity and parameterized decision problems. And then I kind of started the polynomial, the polynomial state complexity classes. And this talk is actually the continuation of this previous work. Okay, so this is a non-uniform state complexity, the explanation of the non-uniform state complexity classes. So the 1D stands for the set of families of the promised decision problems, so that we can actually pick up the family of polynomial state one-way deterministic finite automatons, and that actually solves those given promised decision problems. Right? So this is the 1D, the D stands for the deterministic. So we can actually think of the non-deterministic version, or bounded error probabilistic version, or unbounded error probabilistic version, right? And so on. But here, the state complexity is a polynomial. But then if you just use the exponential state complexity, then we'll write 2 to the 1D, just the notation. Well, I didn't study those notations, but the people started using it. Well, here then I come back to the discussion of the deterministic and non-deterministic cases, right? But here, well, we know that the deterministic finite automator, the non-deterministic finite automator is always translated and converted into a deterministic finite automator. This is just the probably the first class of the finite automata theory in the university. But here, well, the situation is different because they're actually using some constant number of states, right? But here is a polynomial. So in that case, we have the separation between 1D and 1N. So that's the main difference, right? So this is about one way. But now we actually move into the 2A, right? So we write 2D, 2N, and so on. The 2 stands for the 2A head moves. Now the 1D head moves and the 2A head moves are different. Well, although in the constant state complexity classes, this is a uniform model, right? And 1DFA is exactly the same as 2DFA, so everybody knows this, right? But then we have the separation here. This is exactly what I said before, right? In a 2A deterministic case and 2A non-deterministic case, we don't know whether both classes are exactly the same or not. But then if you have assumption like this one, NN stands for the uniform model of the logarithmic, non-deterministic logarithmic space class. So this is not included in the deterministic logarithmic space with some advice, the polynomial side advice. If this condition holds, then we will get this one. Okay, so we just simply take the quantum version of all those complexity classes. It could be possible, right? We simply replace the machine model by the quantum finite automata. So we will get 1BQ, and so this B stands for the bounded error, right? Here, the bounded error case. The Q stands for the quantum. So we have a whole bunch of things. So interesting thing is we have the inclusion and the separation results for some classes, not all classes. So this thick arrow stands for the proper inclusion. So as I said, the 1D is different from 2D, for example, right? The 1D is different from 1N. So we have a complete separation here in some places, but not many locations. For example, then we don't know the separation between the 2BP and the 2BQ. So this is the probabilistic version, classical probabilistic version. This is the quantum version. Right? Well, here, 1.5BQ, so this is just, well, if you're not familiar with the quantum stuff, then you might be wondering what that means. Then 1.5 is just location, is located between the one way and the two way. Because then one way, I mean that the head always moves, right? If you allow the head to stay still, right? So that is kind of in between the one way and two way. So that's right. Okay. Well, in a deterministic case, it doesn't matter, right? Whether you actually allow the head to stay to take a stationary move. But in the quantum case, situation is different, right? Now you see that the quantum case is, somewhat strange, from the classical point of view. Right? Okay, now I'm going to introduce the super quantum finite part. Do you remember in the transition table? The software, we actually fix the transition table, and then just we run the machine, right? Based on it. Now, what happens if you take a superposition of the transition tables? We have a quantum state of the transition tables. The machine actually can access each individual quantum table and then start make a computation. In a quantum computation, you could possibly make kind of the crossing out some positive or negative amplitude. Right? So it could possibly we can do much better than the just a single transition table. But to make make use of most use of this the superposition of the transition tables, then we allow the machine to erase the transition table. Suppose the transition table itself is written on some tape, and whenever it's an access the quantum table, then after before the termination, you just simply erase everything, so that that all the interference, quantum interference, take place, right? But the problem here is that I just will simply write using a small s to stand for the super, right? Now I don't know whether the super 2QFA is better than 2QFA in a polynomial state complexity level. Okay. Now I'm going to going into the main topic of this talk, relativization. The relativization is the another way to convince the people that we actually do better or less better than the others, right? So to do so, we actually generate an oracle. So machine always can access the external information source called an oracle, right? It could be a set or it could be a function. So whenever the machine is stuck into their computation, they just make a query. Well, tell me what it is, or tell me whether this the outcome of this function is. So an oracle actually return the answer to the oracle machine. So an oracle machine receiving this information just continue doing the computation. So the process of the computation is something like this. Well, the machine with oracle, the oracle machine can make a query and receive the answer and then continue the computation. Just to make just to repeatedly make queries until it terminates. Well, why we need relativization? Or suppose that we get a whole bunch of relativized results. What does that mean? Or what does that imply to the state of the complexity. So for example, then we'll take a look at the PNP question. Though this is one of the famous questions in the mathematics and complexity theory, right? Also. Here, in 1975, Baker and Gill and Solvay, they introduced the notion of the relativization, and they constructed two oracles. So this is the polynomial time complexity class, using the access to the oracle A, and this is actually the non-deterministic version of it, right? So the P to the A and the NP to the A, so both are exactly the same. And also they created another oracle saying that the P to the B and NP to the B are different. So the very conflicting result, right? So this is actually the fact that the most known proofs, there's the very clever proofs and the very simple proofs, and there are a whole bunch of different proofs used in the computation and complexity theory. But those proofs are relativizable. That means that if you just take a look at the proof, and then you can just add the oracle, but still the proof works, right? So if you want to try to P equal NP question, either the equality or inequality, right? Suppose you try to prove those things, right? But then if you come up with the proof idea, but if that is based on the well-known proof ideas or techniques, but they are relativizable, that means that those ideas doesn't work because it's make a contradiction with this result, right? So you have to have a really innovative idea to attack those questions, right? So this is just one suggestion. Well, the relativization result tells you that well, if you're looking at the very simple proof idea, it doesn't work. Okay. Now, the same thing is well, here I'm going to explain about the two different kinds of oracles. I'm talking about the quantum computation, right? And we are actually using the classical oracle and also the quantum oracles. The classical oracle is just a simple set or a function, okay? The oracle machine produces y and b. B is just 0 and 1, and the query word is y on some query tape. So we just attached an extra tape called the query tape to the finite automata, quantum finite automata. And M make a query to the oracle A. Then oracle A returns the answer, A of y, the value associated with y. But in the way that the oracle changed this state into here. So this notation is an XOR. So the A of y XOR b. So that's the outcome, or the answer from the oracle. Now the quantum finite automata start reading this one and then continue their computation. But before that, before making the second query, they have to erase everything because we only have one tape, right? So that's the must. Okay, so now the quantum oracle. Quantum oracle is basically our transformation or unitary matrix, I might say. So the machine can make a query in the form, just to write down the query word y on the query tape. The oracle, so this is the transformation or function, right? So they change the y into the u of y. Well, the suffix, subscription n stands for the nth or the parameter, because we're actually talking about the primaries of the machines, and also we have the primaries of oracles. Okay, so this is just a simple example of quantum oracles. This is a transformation, right? And suppose we will get query word psi and x. Well, psi is could be a quantum state, right? Now, if psi is exactly the same as the first fixed quantum state, then we simply add extra phase, the -1 to the L of x. The L is the actually fixed language, right? And so otherwise, we just simply apply the identity matrix, right? So this is the quantum arc. So we simply change the phase, right? But the words do not change. Well, this mechanism is not realized in the classical sense because then we can't change the phase. Right? Okay. Now I'm going to explain about the main result of my talk. Right? We just go back to the well. This is just the extract of the result. Oh, the time is getting running out. Okay, so just a few things. Now we don't know the inclusion or separation of the complexity classes. Now we add try to find an artwork that actually makes the separation and also the collapse. For the well, because we are actually dealing with the amplitude. Amplitude is usually any complex numbers, but then some complex numbers are not computable, right? So we have to put some restriction. We are actually using some only approximable, computationally approximable amplitude. Okay, so those are the results. So we have two different articles that actually satisfy this condition and also satisfies another condition here. If you just make a comparison between an A and B, so we have the very conflicting results, like P and P question, right? And another articles that actually make another conflicting result here, right? And the third one, we have the actually constructed the oracle, quantum oracle that separate them two complexity classes. So the quantum transition table, well, the superposition of the transition table, the use of that table is much more powerful than the just a single quantum transition table. Right? So what is this oracle? So that is exactly the same as the quantum oracle I showed you in a few slides back. That simple quantum oracle make the difference. Okay, so this is the challenging open problem. So we have the number of tables. The main goal is to prove or disprove the inclusion and the separation of the all complexity classes without any oracle. That's the final goal. But it seems to be really tough because our result, well, the relativization results said that simple proof doesn't work. The simple idea doesn't work. You have to really, really come up with a new idea if you want to attack those questions. Right? And also we introduced the previous paper introduced Turing reduction, so that we can have the 2D to the 2D. Those are complexity classes, right? And we have a collection here, but 2BQ we have the separation instead of this one. Well, in the polynomial time complexity classes, and BQP to the BQP is then the BQP. So we have some difference between the finite automata case and the polynomial time the Turing machine case, right? For the quantum setting. Well, thank you for listening, and I'm happy to take your questions.
Thank you very much. I'm sorry. So the talk was very nice, and I forgot to control the time.
Okay. No, that's fine. That's fine. Okay. Well, thank you very much.
But I think we can accept a few questions.
Oh, sure.
Yeah.
Okay. Go ahead. Go ahead.
Okay. So I have a question just about notation. So we say you physically erase like some what does it mean? How it's impossible to erase a quantum state. Right. What exactly do you mean by erasing, physically erasing something?
Well, So you're talking about the quantum finite automata itself?
Quantum finite automata, if we go through slides back, I can show.
Oh, sure, okay.
So was there not talking about oracle quantum?
Oh, quantum oracle, okay, sure.
Yeah, it was like y and oracle to y. I'm going to say you erase it.
Oh, this one, right?
No, I think before that.
So this is the example to the quantum oracle?
No, it's a definition.
Okay.
One more back.
Go back, right?
Yeah, back.
This one, right?
No, I think it went further.
The one with the X.
Oh, slides
Yeah,
back.
one was up, so yes. We should go back.
Go back, okay. Oh, this, oh, sorry. This one?
No,
No,
back.
previous, maybe the previous.
Oh, the classical one. This one?
Yes, this one.
Okay.
So it's point 4. So the machine physically erases both y and.
Oh, I see, okay. I got it to your question.
Yeah.
Okay, so we have one example here that we have a garbage state, right? It's just to simply remove everything into the garbage state.
Oh,
So you can just apply then the tape, right? That is very simple. But then if you produce the y in some quantum way, then you can actually reverse the computation and then just able to erase the tape somehow.
Well, but you cannot erase AY because you don't know AY.
Well, this is just the one bit information. So you just take this one into the internal state of the quantum finite automata.
Okay, so yeah, essentially just move it to rubbish.
Yeah, that's right, that's right.
I see.
Okay. So thank you very much again, the speaker.
Oh, thank you very much.
So let's move on to the next talk.